Hello everyone, we're continuing on with chapter 20 with electromotive force. We're also going to talk about standard reduction potentials, so that would be that paper that I gave you with all of the reduction half reactions that are written on them that also have an E value that's associated with them. So we'll do some examples of those. We'll talk about oxidizing and reducing agents today, as well as talking about free energy and redox reaction. So how can we bridge together chapter 19 and chapter 20 and what are their relationships? So let's start off with electromotive force first. And electromotive force we just symbolize as EMF, and ultimately it's the potential difference between the anode and the cathode. And usually when we say like potential difference, we typically think about this as like being the voltage in a cell. So if we think about a battery, the EMF would really be how much voltage something is being able to apply. So okay, so an analogy for electromotive force would be like a waterfall. Now, water will flow spontaneously over a waterfall just because of a difference in potential energy from the top of the waterfall to the bottom of the waterfall. It's very similar in how electrons will travel. So electrons will flow spontaneously through some circuit from the anode to the cathode, and they do this because of a potential energy difference. Now, at the anode, we have a very high amount of potential energy for these electrons. So if I'm looking at my cell right here, at the anode, I have a high potential energy, and that's because I have a lot of electrons here, and ultimately those electrons are going to need to flow through that wire toward the cathode where there's a low potential energy. And just like a waterfall is the same way. We have a high potential energy up here, and then that potential energy is going to be converted into kinetic energy, so we have a low potential energy down here right as it strikes in the pond or the lake or the stream or whatever it's in. So same analogy, high potential energy at the anode, and that means the electrons are going to move from that high potential energy towards a lower potential energy, which will be the cathode. And this happens spontaneously. Okay, so again, we've just defined this on last. Potential difference between the anode and the cathode in a cell is called the electromotive force. We'll see that as EMF. I want you to know that this electromotive force is the driving force to move electrons in a cell. It is the electromotive force. That is the reason why electrons are moving. It's this force right here. Because at the anode, there's a high potential energy. At the cathode, there's a low potential energy. So my electrons are going to move from a high potential energy to a lower potential energy. And the force that's causing that is called the electromotive force, EMF. You may also hear electromotive force designated as cell potential. So it's the same thing. And we'll probably call it more cell potential than we may call it from our book standpoint from this point on, than EMF. So cell potential is just denoted with the symbol capital E and then subscript cell to represent that we're talking about how much electromotive force or how much cell potential we have. And that's going to be measured in volts, which is another reason why we consider electromotive force to just be how much voltage we have in a cell or in a battery. So that should also make sense to us. And 1 volt is going to be equal to 1 joule per coulomb. So joules representing energy and C's coulombs representing charge. So energy per charge is the same thing as a volt. Okay, so in class today, I gave you a standard reduction potentials chart. Ultimately, the magnitude of cell potential is going to depend on the reaction that occurs at the cathode and the reaction that occurs at the anode, because we have half reactions going on at each. At the anode, I have oxidation occurring, remember N-ox, and then at the cathode, I have the reduction step occurring, remember red cat. So I have these two half reactions, but I want to know what's happening in the overall cell. And to find that out, I'm going to have to use something that's called the standard reduction potentials chart. I think yours looks a little fancier and has a lot more on it than this one does. This standard is meaning that it's going to happen at 25 degrees Celsius. We're also going to assume that for standard it's at 1 atmosphere, and we're also going to assume that these are at 1 molar concentration, or 1 molar concentrations. Now, all of these have already been calculated for us, so that's the reason why we just have these, so it's a lot easier. Instead of doing a reaction over and over and over again, we can just say this is the standard, and let's just use that standard every time. When E is positive, my E right here, meaning how many volts do we have? So this would be for all of these are reduction half reactions. So that doesn't mean that all of these are going to be spontaneous. That means that the reduction half reaction, so if E is positive, that means that something is going to occur, or the reaction is going to occur, or electrons are going to travel spontaneously. So when E is positive, this is a spontaneous process, meaning it needs no outside intervention. If E is negative, it's going to be a non-spontaneous process. So when E is negative, that means that these would probably be better oxidizers than they're going to be reducers, if that makes sense. If all of these are reduction half reactions, when I have a positive value of E, that means that these are really, really good reducers. So fluorine is easily reduced. It has a positive 2.87 cell potential for the reduction half reaction. But if I look all the way down here at lithium, lithium does not want to be reduced. I have a negative 3.05. So this is just how I'm reading this chart. We can see here that 0, I have one that's at 0, and that's the hydrogen reduction potential. And the reason that this one is 0 is because we've made it to be 0. So let's talk a little bit about the standard hydrogen electrode. So a standard hydrogen electrode, which you will also hear it known as a She, so just first letter of each one, She. Ultimately, what's happening is we have that's connected. So if I'm looking at this diagram right here, I have a platinum wire that's connected to a piece of platinum foil. So here's my foil here, here's my platinum wire here. And this piece of platinum foil is going to be covered with some finely divided platinum that will serve as an insert surface for this reaction. So I have some, I have my platinum here, my platinum wire here, and then I'm going to stick this tube, because this is all connected in some evacuated tube. Ultimately, I can have a stream of hydrogen gas that's going to come in here on this side. And then I'm going to also have some amount of hydrogen ions in a solution that can be entering in through this way. What we have found when we tried to use this She is that this can operate as an anode, or it could operate as a cathode, meaning that it's possible to go from hydrogen gas to hydrogen ion, or it's possible to do the reverse, hydrogen ion to hydrogen gas. This is one of the only things, or the only thing, only electrode, that's really able to do this. So because it's reversible, we consider this to have 0 volts. Ultimately, it's using everything. It can do the same process in reverse. So it can reduce, or it could oxidize. So it can act as a cathode, it could act as an anode. So for us, we've just defined this as having 0 volts. And then everything else, any other electrode that we've looked at, is just done in comparison to what this She, the standard hydrogen electrode, can do. Ultimately, we just need to know that there's such a thing as a standard hydrogen electrode. It's called a She, and that means that it can act as a cathode, where hydrogen ion is reduced to hydrogen gas, or it could act as an anode, where hydrogen gas is oxidized to hydrogen ion. Okay, so let's say that we want to find the cell potential for the entire cell. I want to know what's happening in the entire and I'm going to find the standard reduction potential for the reaction that's occurring at the cathode. And I'm going to subtract that from the standard reduction potential of the reaction that's happening at the anode. And that's going to give me what's happening for the overall reaction of the cell. So the other thing that we need to do or think about with this is that cell potential is an intensive property, meaning that it does not depend on any type of stoichiometric coefficients. So it doesn't matter how much of something we have, all that matters is what number do I have as my standard reduction potential at the reduction or at the cathode end, and I'm subtracting it from the anode end. So no stoichiometry, no coefficients that I have to take into account. From anode, and then I'll get my overall standard cell potential for the overall voltaic cell. So for example, let's say that we have zinc and hydrogen. So ultimately, zinc in this case is going to be my anode, hydrogen is going to be my She, is going to be on the cathode end. I know that zinc, my electrons are going to flow from the anode towards the cathode. So if at the anode, I have my zinc equation here, and then at the cathode, I have my hydrogen equation here, I want to look up both of these equations on my, or both of these reactions on my standard reduction potentials page. If I do that, I'll find, remember that at the cathode is, at the cathode we have our reduction step, and at the anode we have our oxidation step. For the oxidation step then, I know that, again, that's at the anode, and zinc would have a reduction potential of a negative 0.76 volts. And I know that the She, if I look on that page, is just going to be 0. Forget about this here, because this is for a totally different reaction, so we can just kind of pretend like this doesn't exist. So to find out what the overall cell potential would be, I want to take always what minus what? Remember, I want to take cathode minus the anode. So at the anode we know is oxidation, at the cathode we know that's reduction. So I know that I'm going to take 0 minus a negative 0.76 volts. So ultimately for our overall cell potential, we would get a positive 0.76 volts. And because this is positive, it means it's going to happen spontaneously. For this one, guys, all I did was use zinc, and then I also used copper. So this would be what our cell potential would be for a zinc and a copper voltaic cell or battery. Okay, so let's look at this example. In this case, we see I have zinc and copper, and my zinc is over here at the anode, the copper is over here at the cathode, so we know that the electrons are going to be traveling from the anode towards the cathode, so they'll be moving towards copper. In this it says, for the zinc copper 2+ voltaic cell shown in the figure, we have the reaction that's written out here, so you were given this. I also went ahead and gave you the cell potential, 1.10 volts. Given that the standard reduction potential of zinc to solid zinc is a negative 0.76 volts, let's calculate the reduction for copper 2 ion to copper. Okay, so ultimately this is just kind of doing some different math in what we just did in the last slide. So I know that overall cell potential was equal to 1.10 volts. And I know that my reduction standard potential for zinc is negative 0.76 volts. So this is for zinc. I want to find what's going on here for copper. Okay, well we know that the cell potential is just equal to what's happening at the cathode minus what's happening at the anode. Okay, well, zinc, if I go back to my figure, zinc is here at the anode, and that means copper is here at the cathode. So if zinc is at the anode, I know that this is going to be 1.10 volts equals X minus a negative 0.76 volts. So if I do my math here, I'm going to get X to be equal to a positive 0.34 volts. And if you look on your standard reduction potentials page, we should find that that is the same thing as what copper should be. Next problem. It says the standard cell potential is 1.46 volts for a voltaic cell that's based on the following half reactions here. So using your standard reduction potentials table that I gave you, let's calculate what our what our standard reduction potential would be for the first half reaction. So the overall cell, voltaic cell, has a potential of this, and I can find this one using my table that we were given today in class to find this one, okay? So I'll let you do that one, and we can move on. Okay, and the next one, use the same table that I wanted you to use to calculate the voltaic cell, which is based on the following reaction. So in this one, I've given you a whole reaction, but you're going to have to figure out what are my half reactions, and then let me use my table to find their standard reduction potentials, and then how can I find the overall voltage that's applied for this cell. Okay, so if we did, let's just do the first one together, guys. Okay, so in the first one we have dichromate ion plus hydrogen ion plus iodine is going to make iodine gas plus 2 chromium ions plus 7 water molecules. Okay, so this is what we were given. So first of all, we know that we're going to have to go through and break apart everything into its oxidation numbers. So 6, 2, 1, 1, 0, 3, 1, 2. Chromium goes from a positive 6 to a positive 3, meaning that it becomes less positive, meaning that it must be gaining electrons, so it's reduced. Iodine goes from a negative 1 to a 0, becoming more positive, meaning that it's losing electrons, so iodine must be what's oxidized. So if I want to think about their half reactions, then I think of, I have Cr2O7 going to 2Cr3+, and that would be for the reduction. So this would be my reduction half part, and this is not balanced at all. We're just writing it very quickly. Oxidation would be iodine. So I'm going from 6I minus to 3I2. Okay, so if I want to actually balance them and see what those would look like, oxidation step would probably be a lot easier. So at the oxidation step, I have 6 iodine here, 6 iodine here. So I'm balanced atomically, but I'm not balanced electrically. So I have a charge of 6 over here. So if I add 6 electrons to this side, we'll be balanced electrically as well. Okay, if I look then up at the top one should just be rewritten as Cr2O7. Oh, I forgot my 2 minus there, guys. 2 minus, plus we should have 14 hydrogen ions, plus 6 electrons will give me 2 Cr3+, plus I think we should have 7 water molecules. Okay, so now I have balanced half reactions for each of them. So here's this one, here's this one. Well, I know that reduction half reaction occurs at the cathode. So the Cr2O7 2 minus is at the cathode, and then oxidation occurs at the anode. So this one occurs at the anode. If I look up the values of these two reactions using my chart, I will find that my cathode is going to have a reduction potential of 1.33. And my anode is going to have one of positive 0.54. So if I want to find my overall cell potential, I'm just going to take my cathode and subtract it from the anode. So I have a positive 1.33 minus positive 0.54. So if I subtract those two, I'll get my cell potential to be a positive 0.79 volts. We should throw a unit on that, guys. Okay, so it's as easy as, let's break them up into half reactions, figure out what's the cathode, figure out what's the anode, find my numbers, find those standard reduction potentials on the chart, and then just subtract them. So I think the hardest part, figuring out what's at the cathode, figuring out what's at the anode, because you can easily look at the table and subtract. Okay, the next one, how about you try that one on your own for homework tonight? So it's the aluminum with the iodine. Try that one for me. Okay, on this one, a voltaic cell is based on the two standard half reactions that are given to you here. It says use data in Appendix E to determine which half reaction occurs at the anode and which occurs at the cathode. And then also the standard cell potential. Okay. You probably do not have your book with you, so let's just talk about each one. The cadmium reaction, and then we have one with 10. Sorry, guys. Okay. These are the values of the standard reduction potentials that are given to you for each of these reactions if you were to look in the Appendix E in the back of your book. So they're asking us first, which one is the cathode and then which one is the anode? Now, if something has a greater standard reduction potential, that means it's going to be better at being reduced. So that means it wants to be reduced. So, which one of these has a greater standard reduction potential? Okay, 10 has a greater standard reduction potential, so 10 means that it's going to be reduced. Okay, again, how do I know that? Remember from one of the beginning slides we said that E, when it's positive, means it's going to be good at being reduced. Also means it's spontaneous. So if I'm looking at these two and I want to figure out which one's at the cathode, which one's at the anode, first thing I want to think about is which one's being reduced. Which one would prefer to be reduced? 10 has closer to a positive E than cadmium does. So that means 10 would prefer to be reduced. And if 10 is preferring to be reduced, then that means that 10 is going to be, if this is reduced, means 10 is going to be at the cathode, because remember red cat, and that means cadmium is going to be at the anode, and ox. Okay, the last part of the question was to calculate the standard cell potential. So all I want to do is take cathode minus anode. So we'll do a negative 0.136 volts minus a negative 0.403 volts. And that will give us the overall cell potential, which should be 0.267 volts. And that is positive. Yay! Okay. So talking about oxidizing and reducing agents, the strongest oxidizers will have the most positive reduction potentials. So first of all, let's go back and remember that an oxidizing agent is what's being reduced, and a reducing agent is what's being oxidized. I know it's like totally flipped and kind of messes with us a little bit. But the strongest oxidizers have the most positive reduction potentials, meaning that they're easiest to reduce. And then again, the strongest reducers, the strongest reducing agents are going to be easiest to oxidize. So at the top of your standard reduction potentials page, we probably see fluorine at the top, and lithium is usually always at the bottom. So that means that fluorine, this fluorine gas, is easiest to reduce. So I consider that to be the strongest oxidizing agent. And it's just going to continue as I move this way. So we're increasing in strength of oxidizing agent as we're moving up this way. We increase in strength of reducing agent as I'm looking at the products of the other side of that standard reduction potentials page. So lithium solid is the easiest to oxidize, the strongest reducing agent. Okay, so the greater the difference between, sorry guys, the greater the difference between cathode and anode, the greater the voltage of the cell. So if I have a really strong oxidizer and a really strong reducing agent, then I'm going to have more voltage that can be generated in the cell. And that's just because I'm going to have a larger potential energy difference between the two of them. Okay, so it says using your table, so using your cell standard reduction potentials chart, rank the following ions in order of increasing strength as oxidizing agents. On the second question it asks, rank the following species from the strongest to the weakest reducing agents. So what I would like you to do, I want you to try these two for me. So this is the second question that we'll come to tomorrow at the beginning of class, okay? And this one is easy enough that all you have to do is look at your chart. You only need to look at your chart to try to figure this out. But try to do this first, and then we'll talk about them for sure tomorrow. Okay, so we can also talk about free energy and redox reactions. And I've kept saying, or I've kept alluding to the fact that if we have a positive E, if we have a positive value of E, that means that this is going to happen spontaneously. So a negative value of E is going to indicate that a non-spontaneous process will occur. Okay, so same thing, same idea. I still want to use my standard reduction potentials chart. And it says determine whether the following reactions are spontaneous under standard conditions. So in this case, I want to see what's oxidized, I want to see what's reduced. So if I'm looking here, I have a charge of 0 for copper going to a positive 2 for copper. So it's becoming more positive, meaning that I'm going to be oxidizing copper, but hydrogen is becoming less positive, meaning it must be gaining electrons, so that must be reduced. Okay. There we go. So if copper is oxidized and hydrogen is being reduced, I want to look up their values on my standard reduction potentials chart. If I do that, I'll find for copper and then for the hydrogen one. For hydrogen, we should have 0, and then for copper, we should have a positive 0.34 volts. So hydrogen's just the 0 volts, and then copper is the positive 0.34 volts. And I know that if copper is being oxidized, that happens at the anode, and hydrogen's being reduced, and that happens at the cathode. And we said to find E, we always take cathode minus anode, so this is 0 minus positive 0.34 volts. So in this case, I would end up with a negative 0.34 volts if I have a copper and hydrogen cell. And if it's negative, is this going to be spontaneous or non-spontaneous? It's going to be non-spontaneous because remember, for a spontaneous one, we want E to be positive. Okay, so ultimately for the rest of these, you're doing the exact same thing. So I at least would like you to do B, and if you would like to do A through C down here below, you're doing the same thing, but at least for your homework, I'd like you to do B, and we can check that one too. Is it going to be spontaneous, or is it going to be non-spontaneous? Okay, so how does free energy and how do cell potential relate to one another mathematically? Now, we know that delta G is just our free energy, that's Gibbs free energy, and we have mathematically found that delta G can relate to cell potential by saying that it's equal to a negative N times F times E. E is representing my cell potential. F is just simply going to be representing a constant. It's called Faraday's constant because Faraday is who worked with these flows of electrons. So F is just Faraday's constant. It's given to you here. You will probably more than likely use your joules per mole.
To make this announcement, this year's salutatorian for the class of 2014 is Mr. Daniel Woodall. Please congratulate Daniel as you see him here in the next few days. And our